Hello, Nikolai. Welcome to our academic forum. We are delighted to have you join us today and appreciate everyone's participation in our Freshair Built Environment and Health Academic Forum series. The primary aim of the forum is to provide a platform for young scholars to share their research and ideas. Before the presentation, please allow me to introduce our keynote. I will provide both Chinese and English introductions. Nikolai is currently the Dean of the Faculty of Applied Mathematics and Computational Physics, and he has been working in the field of the computational fluid dynamics and heat and mass transfers application for many years. He has been the project manager in several projects in the areas of heat exchanger design and ventilation modeling. Today, he will present lectures on the topics of experience in CFD modeling of unstandard air distributions in indoor spaces for us. Next, I will provide Chinese introductions. 各位老师、同学，大家下午好！非常感谢大家来参加我们菲兰建筑环境健康系列学术论坛。本论坛由中国环境科学学会室内环境与健康分会主办，中国环境科学学会室内环境与健康分会青委会承办，室内空气质量评价与控制北京市重点实验室和清华大学生态规划与绿色建筑教育部重点协办，主要为青年学者提供学术交流分享的平台。本期我们有幸邀请到了圣彼得堡彼得大地理工大学的 Nikolai 为我们主讲。本期报告的题目是室内空间稳态空气分布的 CFD 建模经验。Nikolai 目前是应用数学与计算物理高等学院的院长和圣彼得堡彼得大地理工大学流体力学研究实验室的负责人，在计算流体动力学、热质传递应用领域工作。主持和参与过多个热交换器设计和通风建模的领域。特别感谢 Nikolai 的答应。接下来我们会把时间交给 Nikolai。Hello, Nikolai. Next, let's welcome your presentation.
Okay, thank you.
Thank you.
So, first of all, I would like to thank Professor Lin for kind invitation, and I'm glad to make a presentation for you. So I am from Peter the Great St. Petersburg Polytechnic University, and here is the picture of the main building of this university that was founded more than 100 years ago. And the outline of the presentation will be as follows. After a brief introduction, I will present some examples of our experience of indoor air environment modeling using computational fluid dynamics techniques, with a focus on the unsteady flow regimes, and there will be some fundamental problems and also some applied problems related to International Space Station modeling. So, but first of all, some background. Our department was founded in 1935 by Lev Gerasimovich Lysansky. Here is the picture of Lev Gerasimovich, the author of the basic Russian fluid dynamics textbook. And now it is a part of a higher school of applied mathematics and computational physics. I am the head of this higher school, but I myself is from the Department of Fluid Dynamics. Now it is the Fluid Dynamics and Heat Transfer Group. The teaching staff of this group is 21 persons, and we have 19 PhD students. And with respect to educational programs, we have about 150 bachelor degree students and more than 40 master degree students with 3 master programs: physical models and high performance computing and fluid dynamics, experimental and computational thermophysics, and the new master program, engineering physics, computing and machine learning. The PhD students studied fluid dynamics and fundamentals of thermo-engineering educational programs. All the educational programs are in Russian. So, our research group, Fluid Dynamics and Heat Transfer Group, specializes in computational fluid dynamics. We develop our own CFD software and in-house code and some specialized CFD-based tools. We solve some fundamental problems in turbulence modeling, in fluid structure interaction modeling, and conjugate heat and mass transfer problems. And with respect to applied problems, we specialize in applications to machinery and power engineering, ship and propeller hydrodynamics, ventilation and buoyancy controlled flows, heat exchangers, and some special blood hydrodynamic problems. I will describe these particular problems, ventilation and buoyancy controlled flows. So, our experience in CFD for indoor air problems lasts for more than 20 years, for about 20 years. So we computed air distribution in ventilated rooms in collaboration with the Freedom University in Brussels and Technical University of Sofia in Belgium and Bulgaria. Then applied problems related to the International Space Station ventilation and to the visiting vehicles like shuttle orbiter ventilation. Then some problems related to ventilation of power gas turbine enclosures and spent nuclear fuel storage ventilation. And also, well, it was a particular problem, but related to our beautiful city, optimization of ventilation systems in the main cathedral, St. Isaac's Cathedral in St. Petersburg. So, most of ventilation systems are characterized by jets, and all applied problems that were presented in the previous slide solved in our research group were multi-jet ventilation systems, like shown here in the slide. It is an airflow in an International Space Station module, Columbus European module, and we see here numerous jets. Only 1/2 of jets, supply jets, are shown here in the slide. And when we have a jet ventilation system, turbulent flow occurs in the ventilated indoor space, and accurate prediction of turbulent airflow is necessary. For example, for thermal comfort parameters evaluation, computational fluid dynamics is a powerful and promising tool for design, but it requires for validation if a turbulent flow is considered. And more important, if we consider unsteady flow with global unsteadiness, validation is really under question. Just background of modeling, we solve Navier-Stokes or Reynolds equations dependent on the approach to turbulence modeling. And here is just a table from a well-known paper from Philip Spallard, a well-known specialist in turbulence modeling, who describes various approaches for turbulence modeling. And in fact, till now, we still use Reynolds average Navier-Stokes approach when we solve a Reynolds equation, and we use some approach to model turbulence, sure it is steady or unsteady Reynolds average Navier-Stokes equation solution. And in this case, we have high level of empiricism. High level of empiricism because we use the Bassanès hypothesis to relate the Reynolds stresses to the mean velocity gradients. For example, the standard Kaplan model by Launder and Spalding is a model based on model transport equation for the turbulence kinetic energy and the dissipation rate. Here it is. It is still used, for example, for jet modeling, because these empirical data, model constants derived for this model were determined based on fundamental turbulent flows, and among them we have jet flow, and standard Kaplan model or some variations of Kaplan model are still used for Reynolds average Navier-Stokes modeling of jet flows. Larger dissimulation approach still uses some empirical data. For example, this model constant evaluation is based on the empirical data for the simplest Smagorinsky subgrid scale model, but this level of empiricism is much lower than for Reynolds average Navier-Stokes approach. So when we use RANS approach, it is still the main tool for applied computational fluid dynamic modeling. We need to validate RANS data, and we may do that using either experimental data or vertex resolving approach results. However, if we still have some empiricism in larger simulation modeling, larger simulation also requires for validation. Unfortunately, there are very few well-documented benchmark tests related to ventilation, and in the experiments available in the literature, propagation of a single jet is considered mostly. Jet interaction is not taken into account, and development of self-oscillation is not considered except this test by Mataui et al. So here are just several tests that were used in our research group for validation of CFD modeling. So the next set of slides is an example of validation of CFD data based on a well-known test for the, let's say, Nielsen rule. These measurements are rather old, more than about 45 years ago. It is LDA measurements in this room, scaled room with one slit inlet or just supply opening and one exit from the computational domain. This test data have been used in more than 50 papers for CFD validation during the last two decades, and we also performed this validation using this geometry model, physical properties, inlet velocity, and the Reynolds number. The Reynolds number is about 5 by 10 power 3. So the flow is turbulent because we have the jet flow. So the turbulence modeling was performed by RANS approach and by larger dissimulation approach. And the meshes were up to 50 million cells for the large eddy simulation, though this problem is relatively simple with respect especially to the geometry. So here are the results of the large eddy simulation modeling. The flow pattern, sure it is unsteady, though it is steady state for the time averaged solution. It is unsteady with high frequency turbulence, especially in the mixing layers, and with relatively low frequency pulsations here in the occupied zone. So here are the comparison of CFD results. We may compare only time averaged data averaged from the larger simulation solutions and averaged from the unsteady RANS solutions and steady state Reynolds average Navier-Stokes solution. And it is visible that we have a relatively good agreement in the jet zone and relatively and worse agreement in the occupied zone with low velocities. However, the main output from these test computations was a special technique that allows to evaluate mean speed distribution based on the Reynolds average Navier-Stokes data. In fact, as it is visible here, we may treat two kinds of velocity. The so-called mean velocity, that is the magnitude of mean or time averaged velocity components. And this velocity is the result of the Reynolds average Navier-Stokes solution. Another velocity is the so-called mean speed, and it is the time averaged velocity magnitude, local velocity magnitude, instantaneous velocity magnitude. And in fact, for, let's say, thermal comfort evaluation, we need to use this second velocity. And it is not possible to obtain this velocity from the RANS solution directly. However, from the large solution, we may obtain both the velocities, and we may derive a correction procedure that allows to compute the mean speed using the mean velocity value and the kinetic energy value obtained from a turbulence model. This addition, like here or here or here, this addition allows to take into account global unsteadiness of the flow that is not predicted by Rayleigh average Navier-Stokes approach directly. So it is visible that there are at least three empirical equations available in the literature. One of them was derived by our research group, and we show that mean velocity processing operates quite well, and the difference between mean speed obtained with this correction procedure and the mean speed obtained directly from the less data, larger dissimulation data, is less than 5% in most of the domain. So here just an illustration of this correction procedure application to the RANS data, and we see that it works. This correction procedure works quite well. So the conclusions from the Nielsen test modeling are, first, that we have good agreement in the jet zone and visible difference between the computed measured data in the low velocity occupied zone, even for this relatively simple problem. Then we show the effective procedure that allows to compute mean speed based on mean velocity data obtained in RANS approach. So then we moved to a seated thermal mannequin test case data. Again, it is the test case from the research group of Nielsen. These experiments were performed in about 20 years ago and 15 years ago. And the main goal of this study is development of a methodology for simulation of non-thermal ventilation problems that arise when people are inside the room, and to test the technique of breathing modeling. However, the experiments were with non-breathing thermal mannequin. So here are the characteristics of the mannequin. They are well described in the same website that is supported by the Nielsen research group. And here is the problem formulation. In fact, it is just a test small room with one large opening, just an open wall, and two small exhaust openings. In fact, with the relatively large velocity, 27 centimeters per second, we have just some example of a thermal mannequin in a wind tunnel. It is not a typical ventilation conditions, but that were the conditions of the experiment. So we performed our initiative simulation for very small velocity, 1 centimeters per second. That was the thermal mannequin under free convection conditions, when, for example, suddenly we switch off the ventilation almost completely, and we have very, very poor ventilation conditions. As for the breathing modeling, we test constant exhalation model and exhalation and inhalation using a sinusoidal law. So here are the computational aspects. Again, unsteady RANS approach and larger dissimulation approach. And I forgot to say that all the results that are presented here in this presentation were performed with ANSYS Fluent software. As I mentioned, we developed also our own unstructured code, but usage of ANSYS Fluent was, in fact, the condition of NASA for the problems with the International Space Station. That is why all this validation modeling was also with the ANSYS fluid. So the airflow pattern is visible here, and as it is shown in the monitoring point velocity evolution, we have unsteadiness, global unsteadiness, mostly due to this bluff body flow passed in a cross flow. So the comparison of the experimental data with the computational fluid dynamics data is shown here. Unfortunately, as usual, for test measurements, we have lack of data, but we reproduced quite well the effect of the thermal mannequin on the airflow and the temperature profiles, except this one in the corner of the room. Then we performed quite large amount of computational runs to study the effect of the thermal boundary condition at the surface of the mannequin, and to study the effect of radiation that is very important for this particular problem. Up to 50% of total heat flux is due to radiation here. So for the mixed condition, for the mixed convection conditions, you see we obtain the thermal plume here, and we obtain the global circulation here in the domain. Unfortunately, we don't have experimental data for these conditions, but this is a very important particular problem. I just mention it here because, in fact, we have a large amount of output from this particular problem of free convection. So as for breathing modeling, again, we get unsteady solution even when we use the constant exhalation model problem. The jet is very unstable, and even Reynolds average Navier-Stokes approach cannot obtain a steady state solution. We have to use the unsteady RANS modeling. In fact, this breathing modeling does not influence much on the flow. Only local differences are detected with as compared with the flow field without breathing model. But it is critical for carbon dioxide propagation modeling, and it is critical to set an appropriate model. For the case without breathing, we may propose the point source model that allows to predict at least something, as is shown here. But sure, we need to take into account these jets to predict the carbon dioxide field more precisely. So I guess I skip here, and here are the conclusions. First of all, we modeled this airflow past the seated thermal mannequin and performed some comparison with the experimental data. And second, we tested respiration models with respect to carbon dioxide distribution prediction. It is necessary to take into account the respiration model to predict carbon dioxide distribution. It is very sensitive to the model. So then let's move to unsteady boundary conditions and formation and motion of turbulent puffs. That is just a pulse jet issued from a nozzle into a free space. In fact, it was the benchmark test. Now it is the direct numerical simulation test, not an experimental test, proposed by a Spanish group 2 years ago, and we participated in the CFD challenge project that was proposed by this group. So we have, first of all, the airflow, and second, the water particles transport. with this pulse jet. In the DNS, some inlet velocity profile was set to reproduce a model cuff, a single cuff, but we tested other conditions and found that they're critical for the initial stage of the cuff, but the far field flow does not is not sensitive to these initial conditions. So again, unsteady RANS approach and large eddy simulation approach, and then again ANSYS fluent and the meshes of up to 35 million cells. And here is the airflow structure when the impulse jet release, and it forms a vertex cloud, and the flow is sure spatially inhomogeneous, and the vertex cloud moves upwards under the action of the buoyancy force. Sure, it could be predicted only with three-dimensional modeling, either large eddy simulation or unsteady Reynolds average Navier-Stokes. The particle spreading is shown here, and as supposed, small particles with a diameter of up to 30 micrometers move along with the Carrier phase, and large particle with a diameter of 130 micrometers or more move along ballistic trajectories. So here is the airflow structure. We proved that Reynolds average Navier-Stokes approach is able to predict the jet and to predict the vertex cloud movement, but the distance of the vertex cloud at the particular time is less with the Reynolds average Navier-Stokes approach, sure due to the initial stage of jet spreading is predicted worse, because unsteady Reynolds Navier-Stokes approach does not resolve mixing layers well, and it over predicts mixing. So here is the position of the velocity maximum for the large eddy simulation solution, and here is the position for the unsteady Reynolds average Navier-Stokes solution. However, if we average the large eddy simulation approach, the magnitude of this maximum is almost the same, and the evolution of maximum velocity with time is also almost the same, but the position is different. So the particle movements again are predicted by large eddy simulation and by unsteady Reynolds average Navier-Stokes approach, well, with the same qualities shown here. So here are the conclusions from the turbulent paths modeling, and also, if we do not need to take into account the buoyancy effects, even axisymmetric unsteady Reynolds average Navier-Stokes formulation can be used to predict roughly the cloud penetration length. So the unsteadiness in the previous case was derived by the boundary conditions, but we can get, unfortunately, sure, for CFD modeling, we can get the situation when the unsteadiness, global unsteadiness, that is not averaged by Reynolds average Navier-Stokes approach, is obtained just due to hydrodynamic instability. And here is the test where we get this global unsteadiness. It is also, like in the Nielsen test, an air supply from a flat slot, and the difference is that we have an open wall, like well here, like it was in the test with the thermal mannequin. But in the test with the thermal mannequin, that open wall was an inlet for the computational domain. And here it is an outlet for this ventilated space. The large box here is just an extended computational domain that was included into the CFD model to predict correctly the conditions here at the outlet. Well, just a comment about this flow regime diagram. It was obtained in the experiments by Mataui and published in 2001, more than 20 years ago. And the unsteadiness depends from the position of the nozzle. So when we put the nozzle here, just in the middle of the domain, then we have periodic self-oscillations that will be shown in the next slide. And if we set the nozzle near the ceiling or near the floor, then we have the steady state flow and we have the global circulation. It was obtained in the experiments by measurement of velocities at several points. So now we may analyze the full flow field using computational fluid dynamics techniques, again, unsteady RANS approaches and larger simulation modeling. And here is the global unsteadiness. It is visible here from the larger simulation computations. You see the jet changes its position from the bottom position like here to the top position in several seconds. And this transition from one wall to another looks like the Quandy effect, but Quandy effect is a stable effect when the jet attaches to the neighboring wall. Now we have unstable attachment of the jet and it changes its position. And on our opinion, the reasons for that are still open. On our opinion, it is just due to this free opening, large area free opening where air exits from the room. So here are just comparison with the experimental data. Again, experimental data were not too rich to compare, and they have some contradictions, like, for example, various periods at various points. But the global problem was caught by this unsteadiness, by these experiments, global unsteadiness, large amplitude and low frequency. This unsteadiness is reproduced quite well by larger simulation data, though larger simulation data predicts more frequencies. This high frequency signal was not predicted by the experiments because the sensor was rather inertial. In larger simulation data, we get these high frequencies, but if we average data over some relatively small periods, like reproduction of some inertia of the sensor, of the experimental sensor, then we get this black curve that corresponds quite well to the experimental data. For this test, during the last 2 years, we performed a large amount of methodological computations. First, the extension of computational domain influence on the time period of fluctuations. This extension of domain that was shown previously, it is important. Then two-dimensional approach. Is it possible to model this two-dimensional geometry with the two-dimensional unsteady RANS approach? Well, it is not too sensitive, but we still have some influence of the modeling on the time period. Then the turbulence model, it is more important. You see, we change the turbulence model, and we have more influence than we change two-dimensional to three-dimensional problem formulation. Then the subgrid scale model effect for large eddy simulation modeling. And for large eddy simulation modeling, we also performed the so-called quasi-two-dimensional modeling when we sure large eddy simulation is always a three-dimensional approach. We cannot set two-dimensional modeling. Sure, we can, but the results will be completely wrong. But if we use a relatively narrow computational domain, it is possible to obtain some reasonable data, but we need to check if this restriction, in fact, we do not allow to develop the scale, the vertices with the scale in the third direction that is larger than the dimension of the domain. For some problems, like for example, for the Nielsen problem, it could lead to changes in the solution. For example, for the Nielsen problem that was considered in the first set of the slides, it is not possible to use this quasi-two-dimensional approach, and we proved that in our computations. For this problem, it is possible to do that. So it could save some computational resources, much computational resources. Okay, and then our goal was to evaluate the thermal comfort parameters in this test room and the influence of the global unsteadiness on the thermal comfort parameters. And we obtained this heat transfer problem. And first, before the thermal comfort problem. And we just set relatively cold jet issue to the room with relatively hot walls. And we check if the unsteady flow regime influences the Nusselt number on the walls. Sure, it influences the Nusselt number as it is visible here. The unsteady flow regime with the global unsteadiness, these are two-dimensional RANS data. And here is the steady state flow regime with the global circulation, and it is obtained with the RANS data. And the Nusselt distributions differ much. This unsteady flow regime results in more uniform Nusselt number distribution that could be important for the cooling problems. And as for the thermal comfort parameters, sure, the oscillator regime with the time averaged fields demonstrates more uniform thermal comfort parameters field. However, sure, the question is still open. If we have this large scale fluctuation, is it locally comfortable for a person inside the room? The question is still open. So then a distribution in a ventilated classroom. We move from the simplified tests to a real indoor environment, though it is also a test. We had a joint project for 4 years together with the team from the Technical University of Sofia, Bulgaria. They performed measurements, and they performed measurements for a real classroom at their university. So with the thermal anemometers and with real supply and exhaust diffusers. Sure, the problem is that the geometry is rather difficult. There are some radiators, there are some columns, and the supply diffuser is also a real supply diffuser, and it is very difficult to reproduce the real conditions. But we tried to do as much as possible in collaboration with them. And here is the result. The result is the problem that I mentioned at the beginning of my presentation. the flow with the numerous jets is unstable, and we were not able to perform largely simulation modeling for this complicated problem. These are just unsteady Reynolds average Navier-Stokes approach data. But even this RANS modeling cannot obtain steady-state solution. The jets oscillate and their pulsations are well pronounced with large amplitudes and relatively low periods. You see, the period is, well, okay. You see the time sample is about 500 seconds, 700 seconds, and the period is tens of seconds and even hundreds of seconds. And it is really a problem for evaluation of thermal comfort and for classification of the indoor spaces. Here are the experimental data. Again, here the sensor, it is a hot wire anemometer technique. The sensor predicts higher amplitudes and let's say higher frequencies than the computational data, because we perform computations with the RANS approaches. And here are the time averaged experimental data with averaging over 60 seconds. And here are the instantaneous draft rate evaluation. And here are the draft rate evaluation for 3 averaging periods. The averaging periods over 60, 180, and 900 seconds. And the problem is that this period influences the draft rate value. And according to standards, it is enough to measure during 3 minutes to collect statistics and to categorize the room. But for multi-jet flow with low frequency oscillations, this sample length is not enough. And it is necessary to pay much attention to the measurement period for a reliable draft rate estimation. Here are the conclusions. And finally, air distribution on board the International Space Station. For the International Space Station, that is rather complicated configuration with several rooms, like one module of the International Space Station is shown here, and they are connected one to another, and each room is supplied with numerous supply diffusers. It is not possible to perform real unsteady modeling, especially under pressure of the design goals. So, for example, here is the computational domain for the assembly, for one of the assemblies of the station. You see here we have the outside view of the station, and here is the pressurized volumes where the crew live and work. And the problem here was that when we have some visiting vehicle, at that time it was a space shuttle that is now retired, but now it could be Space Dragon or other vehicle. We have some vehicle that does not have the carbon dioxide removal system itself. The carbon dioxide removal system is here. So we need to supply relatively bad air with high level of carbon dioxide from this orbiter. And the initial design was that this air is supplied to diffuser A. The modified design, it is supplied to diffuser B. The problem is that to supply air to diffuser B, we need more ducts, and it is very difficult to operate on orbit. And the initial design was simpler. just to have one duct from this orbiter to IMV diffuser A. Here is rather complicated ventilation scheme with some flow rates that must deliver air to the module where to two modules where air is revitalized. So carbon dioxide is removed and new oxygen is produced. It is the US laboratory and the Russian module in the Russian segment. And that is why we have this global air circulation over the entire station. So the airflow boundary conditions were just constant velocities at each diffuser. So in fact, we just keep the flow rate. And the carbon dioxide problem settings. Sure, we were not able to perform this unsteady simulation of development of the carbon dioxide level with the unsteady velocity. So we performed the computations to obtain the velocity field, and then we froze this velocity field and performed carbon dioxide transport problem simulation. And sure, there are crews that produce carbon dioxide with the given generation rate. And also there are systems in the service module, as I mentioned, Russian segment, and in the US laboratory that scrub carbon dioxide, that remove carbon dioxide from the air. Again, ANSYS Fluent, RANS approach, and here are the results. Here are the results. Here are the PET lines from these 2 points. As you remember, point A, diffuser A is in the neighboring module, the module neighboring to the orbiter. The orbiter is docked here, and here are the PET lines issued from B diffuser. So where the air from the orbiter is supplied in the modified design solution. And it is visible that we have noticeable short circuiting. Air from this opening A is not delivered to the hatch to the US laboratory. It returns back to the orbiter. It is visible also here by backward PET lines issued from this hatch. In fact, the flow is from node 2 to the orbiter. We show the backward PET lines, and these backward PET lines have their source in this opening. It is the problem, the short circuiting. Air is not cleaned. It is not the case here because this air does not return to this hatch and to node 2 and then to the orbiter. It moves directly to the return grills, to the exhaust openings, outlets of the domain, and then it passes through the carbon dioxide removal system. Here are the problem: strong short circuiting. And it results in different carbon dioxide distributions. Carbon dioxide distribution, we have various legends, because it is not possible to use the same legend because the level of carbon dioxide is very different. And we have lower carbon dioxide concentration gradients in case B, in the modified design. Here is the difference. Here is the difference. In case 1, we have strong non-uniformity between carbon dioxide level in US laboratory, where we have the carbon dioxide removal system, and in the neighboring modules. Here, in case 2, we have more uniformity in carbon dioxide concentration level. It is just one example of more than 30 problems that were solved for the International Space Station design. And it is just an open question, even for these already solved problems, how to take into account the unsteady effects. And the main conclusions of the whole presentation is that CFD design is increasingly used, as was shown in the last slides, and there are still problems. The quality of simulation themselves often missing, and we may also incorrectly use simulations, and these problems are more pronounced in unsteady flows, and the challenges are that unsteady effects are still difficult for evaluation, and we have performed all these studies at our higher school. Here is our research group 5 years ago, I guess. And the studies were supported by the Russian Foundation for Basic Research and by Russian Science Foundation. Thanks for attention, and I'm open for questions. So, any questions?
Yes. Hello. Can you hear me? I'm Chen He from Tsinghua University.
Yes, I hear you.
Yeah. I have one question for you. As we all know, in buildings, terminal units such as louvers and diffusers sometimes are used as ventilation inlets. However, most CFD
Sorry.
Yeah.
Not good sound. So could you speak? I don't know how. Try to speak again, because there is some noise in the microphone, I guess.
Oh, okay. I'll try to speak again. Well, as we all know, in buildings, louvers and diffusers sometimes are used as ventilation inlets. However, most CFD simulations do not consider the effect of these devices. So, in what extent does this simplification affect the difference between the calculated results and the actual situation? Yeah.
Do you mean the uniform velocity distribution of the diffusers, or what kind of simplification do you mean in your question?
The velocity, yeah, the velocity of the air distribution.
The air distribution, okay. We may simplify the distributions, for example, when we use just uniform velocity profile at the surface of this diffuser, supply diffuser, because sure, we always have some distribution, and it is not uniform in many cases. But I don't think that this simplification is critical, because, as I shown in one of the slides, it influences only in the vicinity of the diffuser, only near the diffuser, but not at the far field, I guess. I guess it is well. It could be used. This simplification could be used. At least we do not know the real distribution almost always.
Yeah.
If I get your question correctly.
Okay, thank you. I just wonder, is there any CFD calculation settings that can take their geometrical model into account? Yeah.
This non-uniformity, Well, only direct solution with the, in fact, with the special duct modeling. I think, in fact, because we usually have some grills. We usually have some grills at the inlet, and these grills their usage leads to more uniform velocity profile, even if we have some bands in the ducts that could lead to the non-uniformity of velocity profile. These grills they lead to more uniform velocity profile at the inlet.
Okay, I got it. Thank you. I have no more questions.
Okay, thank you very much. Any other questions?
Hi, I'm Yuki from Tsinghua University. Can you hear me?
Yes, thank you.
I have one question is like less method can bring more accurate calculation results compared to RANS method, but less method often requires a lot of time and computing resources. Most simulations still use RANS method. For indoor airflow simulation, I'm wondering if there is any calculation scenarios that must use less method to avoid unacceptable calculation errors.
Well, in fact, unfortunately, RANS approach does not reproduce mixing layers quite well. So everything depends from the accuracy that is required by the goal of your study. Because as I shown here, for example, especially for this pulse jet, for example, you see the RANS approach could underestimate the position of this vertex cloud by almost 2 times. The same is with the round jets. It is well known that for round jets, let's say the distance at which the velocity has a given value, it is underpredicted by the RANS by the RANS models, by most of the RANS models, because they are not tuned with these round jets, only flat jets. And I guess that we still have to use RANS because just we do not have computational resources. For jet flows, larger simulation gives more accurate solutions. It is without questions. So everything depends from the accuracy that you have to provide, that you need to provide for let's say for your customer. Yeah. For fundamental studies, larger simulation, I guess, are required now for jet flows.
Okay. Thank you so much.
Thank you.
Hello, can you hear me?
Yeah.
I'm Liu Shu from Xi'an University of Architecture and Technology. I have a question. As we all know, accurate prediction of indoor aerosol concentration is important for some situations, such as research the aerosol transmission of disease. Thus, how do less and RANS method affect the calculation result of indoor aerosol concentration? Thank you.
I didn't hear the second part of your question. You asked about larger simulation and what particular What was the particular question?
How do less and rest method affect the calculation result of indoor particle concentration?
Of indoor particle concentration. Okay, it as larger simulation predicts more accurate the velocity distribution. It can lead to another distribution, and it can lead to more accurate prediction of the particle distribution non-uniformity inside the room. So it is typical for indoor particle concentration. So we have more accurate velocity field. We have more accurate time, let's say, time variation of velocities, and due to that, indoor particle distribution differs when we use less as compared with the Reynolds average Navier-Stokes approach. Sure, any quantitative estimations, any quantitative evaluations again require for some test computations with the particles.
Thank you. Can you hear me?
Yeah.
I have a question that I would like to ask you. Are there any new methods that can make CFD simulation of indoor air flow more accurate and faster, such as combining machine learning with CFD?
Combining what with CFD?
Machine learning with CFD.
Well, I did not catch the idea. What can we combine with CFD?
Are there any new methods that can make CFD simulation of indoor air flow more accurate and faster, such as combining machine learning with CFD?
Machine learning.
对对对。
Well, you see, machine learning does not influence accuracy. Well, it can as you mentioned correctly, it could reduce time for obtaining for making a decision because we may just reduce the number of computational runs when we use these machine learning approaches. But on my opinion, it is still an open question. As I mentioned, we just open a master program and we are on the way to understand these machine learning approaches in CFD. We have experience in our research group on machine learning application to tuning of the turbulence modeling. For example, we may improve the values of the empirical constants in the models, and it is one way of using machine learning. We have experience in it, but this experience is not too good because machine learning is a formal procedure, and each empirical constant in the turbulence model, in fact, is not a formal constant. It was obtained by analysis of the physics of the flow, and well, just using some test cases and using information from these test cases with the machine learning techniques is, well, it is not a way to improve these constants, on my opinion. Another way is to set, let's say, several computations, use information from these computations with various, for example, various constructions with various diffuser shapes, etc. And then using the machine learning technique without additional CFD computations, optimization of this shape, for example. It is a promising way, on our opinion, but we still did not have much experience in it. We have only one, I guess we have only one example of application of machine learning techniques to optimization of turbomachinery device. It is not related to indoor air applications. Okay, so only just general words with respect to these machine learning problems for now.
好 ，OK, thank you very much.